This video is going to walk us through the comparing two population means topic. The idea here is there's two different populations that we're working with, and they both have a population mean that we're interested in comparing. Up to this point in time, we were working with either a single population mean or a single population proportion. Well, now we want to compare two. Answer questions like, which battery lasts longer on average, Energizer or Duracell? We're going to look at a couple different ways of comparing two population means. Our goal here is to learn about the relationship between the two means. Is one mean bigger? Is one mean smaller? The way that we're going to do it is to use the two tools that we've been working on over the last several weeks, confidence intervals and test the hypothesis. We're going to see a lot of similarities between the topics here in Chapter 7 and the topics we've looked at in our confidence intervals and test the hypothesis material. So a lot of things like rejection regions, p-values, sample size determination, assumptions, a lot of those things are going to come into play. We expand our knowledge a little bit. In the first place, we'll see that when we get to our confidence interval interpretations. But a lot of the same ideas are going to move forward. So if you're feeling good about what we've seen so far, comparing our confidence intervals, test hypothesis, I hope you won't find too much challenging material. There is a little bit. There's one topic in particular we're going to talk about on this video that's extremely challenging, so we'll get right into it. All right, first, before we start, there are two different ways of doing this analysis. Again, we're trying to compare means. What I'm going to speak about in this video is the independent sampling technique. So we'll call that regular capital letter A, not Roman numeral, capital letter A. We're going to look at independent sampling, and this is where we're randomly and independently sampling from two target populations, much like you've done on your projects. You've got two different groups that you sampled from, and you want to compare the results. We want to compare the means for the two groups. Later on in this chapter, we'll talk about comparing the proportions for two groups when we're working with qualitative data. But when we're working with means, comparing two means, independent sampling is what I'm going to talk about here. There is another analysis. Sometimes you can pair the information together. Couple names. Paired difference analysis, matched pairs design, dependent samples. Three different names that I can use interchangeably. Typically, I'll use the paired difference or the matched pairs analysis if I want to explain that. I'm not going to address that in this video. When we get back in class, we'll take a look at that in another lecture. Right now, we're going to study the independent comparisons of means. And so let's just jump right into that. When we're working with independent sampling, we can look at a confidence interval. We'll come back and look at a test in a second. But think back to the confidence intervals we've seen before. There's always been a formula, x bar plus or minus z alpha over 2 times sigma over the square root of n. We've seen some work with proportions. Here we're just expanding that. We're comparing two means, so we're going to look at two sample means. Now, I can work with a z distribution, but we've also seen where we can come in and work with the t-distribution as well. That's going to be a sample size question. Large sample or small sample when you're working with means. What would you expect it to be? Hopefully you're thinking 30 or more. In this case, both samples have to be 30 or more to be considered a large sample. If you have one large and one small, we'd work with the t-distribution. That's a small sample problem. But we're going to be working with a formula. Again, you're not going to be expected to do this formula. These are going to show up as endpoints, numbers, upper and lower endpoints on a printout. And I'll show you how to work with the statistics printout in just a bit. However, we're dealing with a difference between means. Think about this question. What is the value of that difference if the means are equal? And that's what I've put here in this little statement. If mu1 and mu2 are equal, then the difference is 0. How we interpret this interval, the relationship between the means, really we're asking the question, which mean is bigger, which mean is smaller? Are they the same? Do they differ? The interpretation hinges on where these endpoints fall. Specifically, when we're looking at the value 0, does 0 fall inside the interval? Does it fall outside the interval? And so our interpretations that we see when we're comparing two means are going to be very similar to the questions that we answered when we were interpreting intervals earlier. I would give you a confidence interval for mu. There was a practical interpretation, there was a theoretical, and then I came back and say, well, is the value of mu equal to 52? And you'd have to look to see, well, is the value 52 inside or outside that interval? And the way you answered that question depended upon where the value I asked you about fell. Now I'm only going to be, or I'm typically, I shouldn't say only, but most cases I'm only going to be interested in about the value 0. Does it fall inside the interval or out? So as I go to this interpretation. If, now what does this mean? If the endpoints, remember we're going to be getting, we want to find out, we're going to be asking the question, is this difference equal to 0 or not? If you have two positive endpoints, well that means that the difference between the means, if this confidence interval goes from like the values, say 10 to the value 20, if that's your confidence interval, what we know is that the difference between mu1 minus mu2, well that number is greater than 0 because all the intervals, this is a positive, and this is the way I'm thinking of this interval, it's two positive endpoints, a positive lower endpoint and a positive upper endpoint. The difference between the means is greater than 0. Our conclusion is going to be mu1 is bigger than mu2. Now the opposite case would be when you have two negative numbers. So you have, say, negative 40 as the lower endpoint and negative 30 as the upper endpoint. In this case, you have two negatives, and the way that I would depict this interval is this is one that has a negative lower endpoint and negative upper endpoint. That's what these things over here are representing. In this case, we would say we're 95% confident, or whatever our reliability level is, that mu1 minus mu2 is less than 0, and so our conclusion is going to be the first mean is less than the second mean. Now, interesting, at least to me, when I look at this interval, my conclusion is going to be mu1 is bigger than mu2. I don't know what mu1 is. I have no idea. It's just saying mu1 is somewhere, we're 95% confident mu1 is somewhere from 10 to 20 units bigger than mu2. I don't know if mu1 is 100 or 1,000. I have no idea. We're not interested in the specific value of mu1 or the specific value of mu2 when we're looking at these intervals. We're just trying to understand the relationship between them. Now the third case, what happens if your interval went from, say, negative 10, that's your lower endpoint, to positive 20? Oops, let's try that again. There we go. Negative 10 to positive 20. This negative number indicates that mu1 could be less than mu2. This positive upper endpoint indicates that mu1 could be greater than mu2. And so what we're going to say in this case, where we have a negative lower endpoint and a positive upper endpoint, we can't determine which mean is bigger. And here's the question. Where's the value 0 when you look at this interval? Doesn't it fall inside the interval? Sure it does. The value 0 falls inside this interval. It's outside this one. It falls actually below the positive interval, and it falls above the negative interval. And so, like we saw earlier, if I asked you if this was your interval, if we're looking at this one here, and I asked you, is the difference between the means equal to 0? You'd say, oh, we're 95% confident the difference between the means is greater than 0. We're 95% confident the difference between the means is less than 0. If I asked you about this interval, though, is the difference between the means 0? You'd say it might be. Maybe at the 95% confidence level, the difference between the means could be 0. It might be negative, it might be positive, but it could be 0. So we just cannot determine which mean is bigger. Now sometimes students say, well, what about the positive lower endpoint and the negative upper endpoint? That can't happen. Numerically, there's only 3 possibilities. And so what you have to do is figure out which of these intervals you're looking at and be able to interpret them correctly. What you realize is that the signs, the positive or the negative signs attached to the endpoints, are more important than the values themselves. Because really it doesn't matter if I said that this interval went from 10 to 20 like I had stated originally, or 0.1 to 0.2, you're still going to make the same conclusion. The fact that every value in that interval is positive is going to indicate mu1 is bigger than mu2. The fact that every value in here is negative indicates mu1 is less than mu2. And again, we're going to be expressing that with our measure of reliability attached to it. We are 90%, we are 95%, we are 99% confident of those conclusions. And so it's a new way, or maybe I want to say we're taking some stuff we've done before and we're stretching it now and giving it a new application. We're answering a question about the interval. Is the value 0 in the interval? And now we're applying that answer to how it works with comparing two means. All right, let's take a look at our test of hypothesis. When we're working with test of hypothesis for mu, our test is going to be that mu1 minus mu2 is equal to some hypothesized difference versus the alternative that, no, it's not. D naught is usually 0. It doesn't have to be, but 9 times out of 10, 99 times out of 100 probably it is. This sign here, yeah, what do you think the other options are? Rather than not equal, do you think we could do a less than? Do you think we could do a greater than? Sure we could. We have the same three choices. You're going to have to figure out which one is appropriate. Can the owners of Duracell claim that their batteries last on average longer than Energizer batteries? And the way I said that, because I said greater than, longer than, you'd probably do a greater than sign, except here's where I'm going to ask you to be careful. I'm going to warn you and say, just be a little careful. If you're Duracell and you want to see if your batteries last longer than, you better take a look at which company is considered company 1 and which company is considered company 2. If company 1 is Duracell and company 2 is Energizer, well, then you would do a greater than test, because you would want to see if the mean of the Duracell batteries is bigger than the mean of the Energizer. You'd do greater than 0. But if Duracell was 2 and Energizer was 1, and you wanted to see if Duracell is bigger, you do a less than test. So you got to be a little careful about the order that you're looking at the populations. Now, when we get to statistics a little bit later on, you're not going to get to choose that order. Statistics chooses the order for you. The way it does it is alphabetically. And so if you had data entered as Duracell batteries and Energizer batteries, they would see the D for Duracell and the E for Energizer, and it would say, well, D comes before E. So it lists D is 1 and E is 2. If you have zeros and 1 in your data set, and I'm thinking maybe towards your projects now, which of those two numbers comes first? The zeros, well, 0 comes before 1. So it's going to list your zeros as your first group and your 1s as your second group. Now, you'll be able to figure that out as you look at your printouts, which we'll see, but it is something to keep in mind. When determining which hypotheses to test, you got to consider which is the first group and which is the second group. Now, with every test of hypothesis, there's our 4 pieces, right? You got a test statistic. The test statistic is the formula part, and I've written over top of it. Sorry about that. That's the part that eventually is going to be a number on a printout. You can try to memorize that formula if you want. I'm going to show you how to get the printouts, or I'm going to give you the printouts when I ask you to do these problems. When you're doing homework problems, I want you to look at the printouts that I've supplied to you. You have to figure out how to make a conclusion. Now, here in your notes, I put the p-value. The computer's going to do the work. It's going to create a p-value for us to interpret. That's true. We could also use a rejection region approach. Figure out which distribution you're working with. Well, if I'm working with a z distribution, guess what my sample sizes were? N1 and N2 would both have to be greater than or equal to 30. That gets me to a z distribution. If I don't have a z distribution, well, then I'm going to be working with a t distribution. And so we have the same kind of conversations, the same kind of discussions, the same kind of topics when we were looking at large sample, small sample before. When we're working with means, we're going to be dealing with M1 and N2. When we're working with proportions, we're going to be dealing with N times P and N times Q are greater than or equal to 15. Here we have to check it versus the value 30. There it's N times P, N times Q has got to be greater than or equal to 15. We'll get to that. You're going to have to make a conclusion for me. Hopefully you're getting good at that at this point. Where are you in that spectrum? If you're writing these notes down, if you're saying, well, alpha is greater than a p-value, reject H naught, and I could actually add the less than or equal to there. If alpha is less than or equal to p-value, we fail to reject. If you're still having to write that, having to put those in your notes every single time and not really remembering, you need to start coming on board. You need to start to remember that, because that's always going to be true. It's one of the reasons we like the p-value so much. All right, so we have our 4 pieces: the test statistic, p-value or rejection region. I've only listed the p-value here, but you could just as easily do a rejection region, and the conclusion. Let's talk about some assumptions. New word for us. We've seen random a bunch. Random. When do we need random samples? Always. This technique requires us to have independent samples. And so our data need to be sampled randomly and independently. On your projects, I know that's how you sampled, so I'm not really interested in those assumptions. Now, the next 2 assumptions that I list are a little challenging. Both populations need to be approximately normal. When would you need this? I said maybe here in your notes. Sometimes you need it, sometimes you don't. You need it if you're working with small n's, small sample sizes. And again, that's with 1 or more of the sample sizes being less than 30. Think about your projects. What do you have? Large samples? Or both? Are both your sample sizes greater than 30? I don't think so. So you're going to be working with small samples on your projects. If you're comparing 2 means, you're definitely going to need this assumption that both the populations need to be approximately normal. And again, populations of what? The x's, the values. What are you working with? Prices? Which prices? State it. Be real specific. Both populations need to be approximately normal. And then the last one, which is the trickiest probably of all three of these, the two population variances need to be equal to one another. Maybe. And this opens up an ugly, ugly can of worms. Okay, when do you need that? Well, walk with me down this road, if you will. Problem that we run into. Let me come back here. You saw a couple formulas. There's one. Oops. Let's go back. Here you go. See this formula here? You got some variances. Go back a couple other pages, or another page of notes here. One more. Bear with me. There it is. We got a formula here. It's got some variances. Every time we've run into these variances in the past, we've seen sigma over the square root of n. We need to estimate them. How do we estimate them? Well, it's a great question. I'm moving ahead here rather quickly. How do we estimate those variances? I think one more will do it. There we go. There's three different scenarios. There's three different ways of estimating the variances. Now I've entitled this Statistics and Estimating the Variance. There's three scenarios that we use. Statistics does two of these really well. If we have large n's, okay, so those formulas had a sigma 1 squared and a sigma 2 squared. I'm going to go through this a little quickly. Now let me do here before I put any notes on this board, because it's going to get ugly when I start putting notes. If you jump ahead in your notes, I didn't give you this next printout I'm going to show you, but if you jump ahead in your notes a couple pages, you'll see this printout. And I'm going to show you how to generate it in statistics. It's very easy printout to generate. You're going to be generating some like this on your projects for me. But when you generate it, down here in this section right here is where it talks about the variances. It gives us two ways of estimating the variances. It says there's an equal variance way and there's an unequal variance way. Now, just keep that in mind. I don't really care too much about that, but let's go back. It gives us two methods, and I'm telling you there should be three. In large n's, if you had large sample sizes, we're going to use a z-distribution for all our inferences, and n would be 30 or more for both n1 and n2. Statistics doesn't give us this option, and so we're going to use the unequal option. Again, I'm going to flip ahead. If we have large n's, we're going to use the unequal option. Now, on your projects this semester, I gave you small n's. One n is bigger than 30, one n is less than 30, but you're going to be working with small samples. And so the option that statistics doesn't give us doesn't apply to you on your projects. This is not going to be what you're going to be working with on your projects. If you did have large n's, you would use the unequal row. And when you use the unequal row, the way that the math is done, this number here would be correct. This number here, the p-value, the confidence intervals, we want to use a z-distribution if we had large samples, and statistics uses a t-distribution. And so it's a little off. It's a tz discrepancy. It usually doesn't affect things all that much. All right. Now, if you have small n's, that's your small n choices. You have two of them. If your population variances are equal, if your population variances are unequal, okay, we must assume that both populations we're sampling from are approximately normal. We need that because we're dealing with small n's. The approximate normal part comes from the small n's. The equal variance part comes from the relationship of the variances. Now, let me give you for instance. Let's give you a scenario here that might make a little sense. Let's take a look. The next time we're together in class, let's take a look in the classroom, and you can see that we have male and female students in the classroom. No surprise there. You've probably noticed it before. If not, there may be something wrong with you. So we got guys and we got girls. And the age-old question is, who's smarter, men or women? Who are smarter in college, men or women? Now, depending who you are and which sex you are, you probably have a different opinion about that. And maybe you say it doesn't matter. But some people have strong opinions. Some people are sexist and they think, oh, the other sex isn't as smart as our sex, and works probably both directions. It's not probably right, but that's kind of how it is. I have an idea. I've been doing this for a while. And so here's how I want to think about measuring it. Let's take a look at the GPAs of males and females. Now, think with me, if you will. When you look at USF, there is a population of all male students. Okay, so think about taking USF's population and segmenting all the guys on one side of the line, all the girls on the other side. Each of the students there has a GPA. And so if I really think about it, when I look at the population of male students, there's an average. There's an average GPA of all the male students. There's an average GPA of all the female students, and that's what we're interested in comparing. That's what we're doing in this section, trying to compare population means. All right, good so far? I think so. Now, as you look at those male students, let's focus on the guys. If I asked you the question, what's the GPA of the smartest male, I think you would tell me it's 4.0. What's the GPA of the dumbest male? Using kind of a nasty term, but what's the intellectually challenged male? What's his GPA? Now, a lot of times people will say 0, but it's not really 0. What's the lowest your GPA can be and still consider yourself a student? After a while, you become an X student. The lowest GPA of guys on campus is usually around a 2.0. GPAs range between 2 and 4, typically. Can you have someone who's a little lower than 2? Yeah, maybe, but for all intent and purposes, 2 to 4 is where the GPAs rule. And the average GPA of the guys is going to be somewhere around 3. It's just the way it works. When you look at the females, it's pretty much the same, isn't it? The smartest female has a GPA of 4.0, and the not as smartest, the intellectually challenged, the dumb female, the lowest GPA female walking around is probably around 2. And so here's what I'm going to challenge you with. When you look at the variation in the GPAs of the men, and you look at the variation in the GPAs of the women, I'm going to challenge you to say that those variations, those variances, those population variances are probably the same. The spread of the data is probably the same for the males and the females. The middle of the distribution may be off a little bit. One of the populations, the males or the female population, may have a slightly higher mean than the other. And so if we took small samples, in that case, it may make sense, and I'm going to give you a more concrete way of comparing and trying to figure out the variances, but it may make sense to assume that the population variances are equal. If that's the case, then when I flip to that statistics printout, we're going to use the equal variance row. We're going to use this test statistic, we're going to use this p-value, and we're going to use these confidence interval endpoints. If we can assume that the variances are equal. If we can't assume that the variances are equal, well, then we're going to use the unequal variance row. Now let me go back to that page just a second. So if we have small n's, we got to consider the variances. That's just the way it works. Large n's, you just use the equal variance row, you use the unequal variance row, and you're good to go. The p-values are off a little bit. The confidence interval endpoints are off a little bit, but by and large, it works pretty well. When we have small n's, we got to really consider the variances. If we assume equal variances, whoops, that was supposed to be circled or underlined. If we assume equal variances and use the equal variance row, we still have to assume that the populations are approximately normal. If we don't assume equal variances, if we assume that they're unequal, we won't make that assumption. That's why in your assumptions right here, I said you may be assuming equal variances. You may be assuming approximately normal. It depends. What's your sample size? Here, the only way you would assume that you have equal variances is if you had small samples and you needed to assume equal variances. Okay, so the question is, there's your printout again, how do you assume, or how do you know whether to assume the variances are equal or not? Again, the only time this makes sense, the only time you have this conversation is if you're working with small samples. And I did it now. Let's go back. Small n's. That's the only time this makes sense. We're going to test the variances. Now, this is a test we haven't seen before. We're going to test to see if the variances are equal. That's what the null says, and the alternative says the variances are unequal. And so we set this up. Now, this is actually on the printout. It's called the folded F test. Let's go back to that printout. It's right here. Homogeneity of variances, the folded F test. This is a test to see if the variances are equal. Here's your test statistic. It's an F. What the heck is that? I don't care as long as we know how to interpret a p-value. Can you interpret a p-value of 0.26? I can. Alpha, whatever alpha we choose, is going to be less than that p-value. For this variance test, I would choose an alpha of 0.10 whenever you're doing the variance test. You're going to fail to reject. There's insufficient evidence to reject H naught. Let's look ahead. What does that mean? There's insufficient evidence to reject H naught. We can't say that the variances differ. We're going to go and use the equal to row. When the p-value, and we should put greater than or equal to, let me put the equal sign in there. When the p-value on the folded F test is greater than or equal to 0.1, we fail to reject. We use the equal row on the printout. If that p-value is less than 0.1, we use the unequal row. So let me go back to that printout again. What we're going to do, and I got a lot of marks on this printout. Let's see if I can. There we go. Start all over again. Oh, I didn't really want to do that. All right, so I'm going to do it this way. You start here. When you have small samples, you look here and you see samples of size 6. You start here at the variance test, and you say, you know what? Because that variance is 0.26, because it's bigger than 0.1, we fail to reject. We're going to use the equal row. So when I ask you for a p-value, 0.0780 is the correct p-value. This is your endpoints, the negative 1.1225, the 6.0892. Those would be the endpoints you use for your confidence interval. We do a test to determine what test to do. It's crazy. Did I mention it was confusing? Let's take a look at a couple examples, and hopefully we will alleviate some of this confusion. So let's go and take a look at example 8.10. Independent random samples from approximate normal populations produce the following results. Look, we have two samples. We have sample 1 information here and sample 2 information right here. And what we want to do is compare the means from the population that these two samples were selected from. So we want to actually test to see if the mean of sample 2 is bigger than the mean of sample 1. Isn't that what that's saying? Mu2 minus mu1 is greater than 0. We want to test at alpha equal 0.10, and we want to create a 98% confidence interval for the difference in means. And so what we first have to do is figure out what it is we're going to test. And so coming up with the null and the alternative. Now, typically we write the null and the alternative in terms of mu1 minus mu2. So if we want to show that mu2 is bigger than mu1, isn't that the same thing as saying mu1 is less than mu2? And so that's how we're going to write it. And sometimes students get confused with the order, like which one's the first one, which one's the second one, how's that change the sign. But think of it this way. For most of the students that I teach these days, I'm older than that. And so you can think of it in terms of if we take your age minus my age, that's going to be a negative number, isn't it? Because most of the students are in their late teens, 20s, and I am a tad bit older than that. So if you take your age minus my age, you're going to get a negative number. Whereas up here, when we flipped it around and put me as the first person, and took my age minus your age, you got a positive number. So you can kind of look at it a couple different ways. Well, the way that we're going to write the null and the alternative is always going to be mu1 minus mu2. And so we want to specify the alternative that way. If we're doing a not equal to test, if we're testing to determine if there's a difference, it doesn't matter. But if we want to show that one mean is bigger than another mean, we always have to consider which one's the first group, which one's the second group, and how's that going to impact the less than or the greater than sign. So in this case, if I want to show the first mean is bigger than the second mean is bigger than the first mean, which is really what they're asking us to do up here, we're going to do a less than test. Now we need to go to statistics to generate a printout. Now I'm just going to show you what that printout is right now, and then I'm going to come back in a little bit and I'll show you how we do that in statistics, how we generate the printout. But this is the printout we're going to get. 2 sample t-tests for x by a variable called sample, and we have sample 1 and sample 2. You can see they're listed right here. You're going to see when we get into statistics that you don't get to choose the order of which is the first group, which is the second group. Statistics is going to choose that, and it's going to do it alphabetically, and because 1 comes before 2, it lists 1 as the first and 2 as the second. The sample information is going to be given in the top part of the printout. This is the test that I asked for. When I get into the menu, when we get to statistics, I'll show you how to generate the menu or create the menu and go in there and specify the test you want to conduct. But really the question that we've been talking about is which row is important to use, which was the right row to use here. And we start by considering the sample size right here. If we had large samples, we would just go and use the unequal row, but of course we don't. Both of these sample sizes are less than 30, and so before we consider the relationship of the means, we got to come down here and consider the relationship of the variances. We have to do that variance test. We have to go back to that last sheet. Let's go back. There it is. We have to do the folded F test, and we got to look at the p-value on that folded F test. So I'm going to come down here and I'm going to look at this number right here. Because that number is big, we're going to use the equal row, because this p-value right here is bigger than 0.1. we're going to use the equal row. Now, in terms of the test statistic, right here, in terms of the p-value, you can see that it really doesn't matter which row we'd use, does it? Because look, those numbers are the same. Well, on this printout, it doesn't matter. But how about a future printout? Do you think it might matter in a future printout? Of course it will. And so those are the numbers that you're going to see me transfer over here. The test statistic is negative 5.12. The p-value is 0.0000. Now, it's probably 0.00000002 or some small number. But really, when they're this small, our conclusion is going to be reject the null hypothesis. Any alpha, they ask us to use a 0.10 here, but an alpha of 0.01, we'd be able to reject H0. There's sufficient evidence to indicate the mean for population 2 exceeds the mean for population 1. If you wanted to say that there's sufficient evidence to indicate the mean for population 1 is less than the mean for population 2, that's fine too. That's completely fine. We're using our p-value to make a conclusion. Now notice we didn't use a rejection region approach. I think we're starting to see that the p-value approach is a better and is maybe easier. Better is probably not the right word because the rejection region would get you to the same conclusion, but easier way of making a conclusion. Okay, so a test is comprised of the four pieces: the test statistic. Now we're looking at p-values and the conclusion. You're responsible for all four of those. All right, in part B it says take a look at that confidence interval, create the confidence interval, and we can do that right here. And you can see that there is a little bit of a difference between the two rows here. The negative 14.842 and the negative 5.2083. Now, that's the confidence interval for mu1 or for mu1 minus mu2. If we want to create the confidence interval for mu2 minus mu1, everything kind of gets flipped around. It becomes a positive 5.2083 and a positive 14.842. And so now we're going to be interpreting a positive interval, and we talked about this a little earlier. We're going to say that we are 98% confident the mean of population 2 exceeds the mean of population 1. We're going to end up with the same conclusion we had for our test hypothesis. Now, if I took the confidence interval off the printout, if I took this one, the two negative endpoints, we'd be making a statement about the confidence interval for mu1 minus mu2. Our conclusion would be that we're 98% confident that mu1 is less than mu2. So again, mu2 exceeds mu1. Mu1 is less than mu2. You can say it either way. You can say it either way. And so that's a good example of a comparison, an independent comparison of two population means. Let's take a look at one more example here. I'll go to the supplementary problems. Exercise 8.109, we're collecting data for toothpaste. Buyers and non-buyers of Crest toothpaste. And in the book, they're going to show you the data set, I believe, where they're asking you, how old are you? And what kind of toothpaste do you buy? And we want to compare the mean age of buyers and non-buyers, of purchasers of Crest toothpaste and non-purchasers. That's what the N and the P. Now again, because N comes before P, statistics is going to choose N as the first group. So really the printout here is a printout of mu N minus mu P, the mean of the non-purchasers minus the mean of the purchasers. Now the question I have for you here, now you don't have any questions obviously in the problem yet, we'll get them on the next slide. Which of those two rows is going to be the appropriate one to use? That tends to be the most confusing part of this whole process, figuring out which of those two rows is the appropriate one to look at. And we start again, we always consider the sample sizes. Again, I have a small sample case, 20 and 20. Okay? Think about your projects. What are you going to have in your projects? When I ask you to do a similar analysis in your projects, you have two different levels and you have two different sample sizes. Are they both 30 or more? I don't think so. I think you have one that's large, but you also have one that's small. And so you're going to need to consider that a small sample problem. In order for us to have a large sample problem here, both sample sizes have to be 30 or more. And as soon as you know that you have a small sample problem, one or more of the sample sizes is less than 30, we got to come down here and we got to consider the relationship of the variances. Now, unlike the last printout, when we looked at the last printout, what was this p-value? Something like 0.4811. This is a smaller value now. And so I'm going to use an alpha of 0.10. I'm going to reject. Remember, this is a test that specifies that the variances are equal. We're going to reject that. We're going to say that the variances are not equal, are unequal. And so we're going to go to the unequal row of the printout. We're going to use this test statistic, we're going to use this p-value, and we're going to use these confidence interval endpoints over here. So now let's go and see if we can answer some questions. So again, I copied the printout for you. And now, do the data provide sufficient evidence to conclude there's a difference in the mean age of purchasers and non-purchasers? Let's do the test hypothesis. Can we conclude there's a difference? What would your no on the alternative be? How do you say a difference? Well, that sounds like a not equal to test to me. And you'll notice I did the not equal to test. Again, when I go to statistics in a little bit, I'll show you how to generate this printout. It's really easy. That's the way statistics writes not equal to. The less than, the greater than. So I have the test. Here's the p-value, 0.0585. What value of alpha would you test at? Well, if you followed the guidelines I gave you in class, how about a 0.06? How about a 0.07? How about a 0.08? Those are all good choices for alpha. You don't need to use the same alpha here that you're using here. In fact, when you do the variance test down here, I'm always comparing this. That's a bad looking alpha. I'm always comparing this to a 0.10 for this test. But then when we go to do, when we want to learn about the variances, we use a 0.10. But when you come up here, you can change to a different alpha. What assumptions are necessary in part A? Okay, I'm not going to go through the test. I want you to do that. Be able to write the test statistic, the p-value. Be able to write your conclusion. What assumptions are necessary? You're using the unequal row. Do you need independent and random samples? Absolutely. Do you need both populations to be approximately normal? Both populations of ages for the two different groups. The ages of all purchasers, the ages of all non-purchasers, both need to be approximately normal. Absolutely, you need that assumption. Do you want to assume that the population variances are equal? No, you don't. You're using the unequal row. If you're using the equal row, you need to make that assumption. So only, no, I should say it this way, one of the assumptions, the equal variance assumption, is not necessary for this analysis. Find the observed significance level. Well, we did that as part of the test up top. We're going to compare alpha to a p-value and make our conclusion. And interpret the confidence interval. Look at the endpoints. 1.0068, 13.793. Two positive numbers. We're going to be 90% confident that mu1, which in this case is the mean age of non-purchasers, is bigger than the mean age of purchasers. Mu1 is bigger than mu2, and we're 90% confident of it. Now you notice that we're pretty close to zero here. That 1 is getting pretty close. If you change this to 95%, I think you're going to get a different answer. Play around with it. Get into statistics and see what you can do. So I didn't write out all the answers to you. I kind of gave you some guidelines and pushed you in a direction. See if you can. See if you can do the test. See if you can write the words. And then when we get back together next time, we'll take a look at this a little bit more. So hopefully that helps you understand how we're going to go and do this comparison of two population means. Probably the most confusing part of it is figuring out what to do with the variance test. Figuring out when you need to use the variance test. Whenever you have small samples, one or more of these numbers is less than 30. So take a look at this, look at some other homework problems, and then contact me if you have any questions. So long. Alright, in this part of the video I want to show you how to generate the printouts that we used in the lecture that I just gave you. There are two printouts that I want to go ahead and generate. The first is where I'm working with the data that comes from the two samples, cleverly called sample 1 and sample 2, and we wanted to compare the two population means. We wanted to see if mu1 was actually less than mu2. So you can see I have two samples of the values of x for those two different samples, and we want to go to the two sample t-test. That's where we're going to be to generate the printouts that we're analyzing in this part of the class. So I'm going to go to two sample t-test, and it's going to ask me for certain variables. It's going to say which variable do you want to actually compare. This is the quantitative variable that you want to compare means of. So we want to compare the mean of the x's. So we're going to put the value x there, and then we want to compare the qualitative variable, even though it's listed as number 1 and number 2. The two levels are the samples. We want to compare the mean of the x's for sample 1 and sample 2, and that's how we set it up. We're going to leave the value 0, which is usually the value of the hypothesized difference. And we said in our example that we wanted to do a less than test. So I'm going to click the less than alternative hypothesis option. In addition, it's asking for a 98%, so I need to change the confidence interval percent coverage to 98. And so then I hit OK. And I think what we're going to see is this is the printout that was generated and used as I went through the class notes. We see the less than sign here. That's what we asked for. And you can see that in this problem, because of this p-value right here, we use the equal row information. And so those were the numbers that we used. And I copied and pasted this and put it back into your into PowerPoint notes. So that's the first printout. Now the second printout is working with the toothpaste data. So let me go and import that and see what we get. So let's go and get rid of this guy. Now I'm going to go and import, and I have all the data sets in, I've listed these in chapter 8, and so it's a CREST file. So I'm going to open that one up, and it's going to ask me what I want to do, and I'm just going to say OK. And we can see that we have purchasers and non-purchasers. Now interesting, to me at least, the purchasers are listed first, the non-purchasers are listed second here, and you can see there's a bunch of them. Yet when we go to that menu, when we go to the 1-2 multi-sample tests, and we go to the 2-sample t-tests, I'm going to compare the ages this time, the ages of the groups. And if I remember correctly, we're doing a not equal to test, and I think we wanted a 90% confidence interval. I believe that is correct. And there's our printout. And because of this p-value, we ended up using the unequal row in this case. And so let me go back to that options. You have to decide what's the variable, where's the quantitative pieces of information. In this case, it was the ages. And what's the categorical, or what's the qualitative variable, and this was the groups. And remember how we said that the P's were listed before the N's. However, when you look at this printout, the N's are going to be listed first because they're alphabetically, N comes before P. And so that's how the statistics decides what's group 1, what's group 2. So you got to think a little bit. If we want to do a one-tailed test, in this case with the not equal to test, doesn't matter all that much which one's the first, which one's the second group. But if you're doing a one-tailed test, like in that previous example, you really got to consider which is going to be called the first group, which is going to be called the second group, and how do I set up my alternative to do the test that we want to conduct. So that's how we generate the printouts, and hopefully that makes sense to you. You're going to be working on some printouts like this for your projects, and you're going to have to go through that thought process. So if you have any questions, you know how to get hold of us. Good luck.